Mathematics is about solving problems, but also tools for solving problems. And one such tool is group theory. If you discover that there's a group in your problem, then you can attack it with all the countless theorems from group theory. But maybe this doesn't completely solve the problem. Maybe our group is not strong enough to do that. In this video, I will show you a technique to get around this. Just transform your group into another, preferably simpler group. The hope is that, during this transformation, the problem simplifies itself and becomes even easier to solve. Here, I would like to look at the three most common types of such transformations: homomorphisms, isomorphisms, and automorphisms. And each technique is simply a more specialized version of the previous one, capable of handling more and more difficult problems. So let's see how exactly they solve these increasingly more difficult problems, starting with the simplest one. Here's a simple problem. Is the sum 16,788,013 plus 9,400,355 even or odd? I hope you're not bothering to actually calculate the sum. Instead, observe that both numbers are odd, and adding two odd numbers always gives an even number. So, hiding behind our equation, there is a simpler equation that gets by only using the concepts of even and odd. Any equation can be simplified by transforming it into either even plus even equals even, or even plus odd equals odd, or vice versa, or odd plus odd equals even. Crazy, right? In group theory, however, we prefer not to use words, but rather groups. Here, the cyclic group Z2 works best. If you recall, it consists of only 0 and 1 and behaves just like even and odd. 0 plus 0 equals 0, 0 plus 1 equals 1, and vice versa. And 1 plus 1 is not 2, but it cycles back to 0. So, whenever we sum two integers together, then there's now also a simplified version. That is, when we calculate, say, this sum here to get 57, because this is odd, it reduces to 1. But since we only care about whether the result is even or odd, 0 or 1, we could do the smarter thing and first translate the two numbers into Z2, because then the calculation 0 plus 1 is much simpler, and it also equals 1. Since we're now using the language of group theory anyway, we can ask ourselves, does this simplification of equations work with other groups than from the integers into Z2? It does, and we call it a homomorphism. Homomorphisms are commonly denoted by phi, and they are defined as follows. They are functions that take elements from one group and output their simplified versions in some other group. But there's one condition though that I like to call the consistency condition. If a and b equals c, then phi of a and phi of b still equals phi of c. This sounds like a reasonable and natural concept, and you've actually seen it before. Let me explain. For example, 1 plus 2 equals 3, obviously. But let's exponentiate 2 by every number here. Then the new equation 2 to the 1 times 2 to the 2 equals 2 to the 3 is still true. That's because exponentiation by 2 is a homomorphism, and it converts addition into multiplication. But how exactly is this a simplification? We know from school that if we have some x and some y, and we want to calculate 2 to the x times 2 to the y, we could do the obvious. Calculate 2 to the x and 2 to the y, and then multiply. But we also learned that we can instead also add x and y, and then exponentiate by that, and yet get the same result. This path requires us to do only an addition instead of a multiplication, and only one exponentiation instead of two. I hope you can see now how homomorphisms are generally used to simplify problems. Funnily enough, the faster path for the even and odd problem was doing the homomorphism first, while for this problem, it is the other way around. But in either case, we now found a common principle underlying both problems that we can exploit. I don't know about you, but when I learned about this, I felt like my third eye opened and I was already wondering where else homomorphisms could be hiding. It turns out they appear quite often. Even just multiplication by, 7 is a homomorphism, from addition to addition. If x plus y equals z, then 7 times x plus 7 times y equals 7 times z. Or here's an example that I hope you engineers will like. The determinant is a homomorphism. I think you get the principle by now, but if the matrices A and B give the matrix C, then the determinants of A and of B give the determinant of C. Although I just want to mention, your textbooks or professors probably give the more compact version that the determinants of A and of B give the determinant of A and B. Before we dive deeper into homomorphisms, I need to explain an important technique. The fact that homomorphisms have to be consistent is very restrictive. Let's look at a homomorphism between Z6 and Z3. And let's say that we already know that phi of 0 is simply 0 and phi of 1 is simply 1. Then I claim that you can infer what phi of 2 must be. We know that 1 plus 1 equals 2, so to be consistent, the equation phi of 1 plus phi of 1 equals phi of 2 still has to be true. Phi of 1 is just 1, and since 1 plus 1 is 2, phi of 2 has to be 2. Likewise, 1 plus 2 equals 3, so phi of 1 plus phi of 2 equals phi of 3. We now know the value for both phi of 1 and phi of 2. Since in Z3, 1 plus 2 cycles back to 0, phi of 3 must equal 0. And so on and so forth. If phi of 3 is 0, then doing the same conclusion gives that phi of 4 is 1, and finally that phi of 5 is 2. This technique of, let's call it reverse engineering, is so powerful in fact that for many groups it suffices to know the values of phi for just a few select elements. In case you've heard of them, for the so-called finite simple groups, even the monster group with more than 808 sextillion elements, it suffices to know the values for just 2 select elements to pin down the entire homomorphism. And here, for the cyclic group, in fact, only 1 element suffices. 1. If phi of 1 were, for example, 0, when we try to reverse engineer any arbitrary number, 4 is an arbitrary number, we can express it with only 1s. That number in the other group, after plugging in for phi of 1, is just a sum of only zeros, and therefore the simplification for this number is 0, and since 4 was arbitrary, it is so for any other number. This reverse engineering technique can, in extreme cases, even determine homomorphisms from 0 information. I mean, from the last video, do you remember the dihedral group? For example, D5 has as elements the 5 rotations from rotating by 0 units over rotating by 1 unit up to rotating by 4 units, and the flipped rotations going from the standard flip all the way up to the flip with a rotation by 4 units. Furthermore, these elements are calculated together in the obvious way. For example, 1 unit rotation and another unit rotation equals 2 units of rotation. Or as another example, a flip and a unit rotation equals simply the flipped unit rotation. And as a final example, if we combine 2 such flipped unit rotations, it turns out we get back the neutral element. There is something I'm trying to hint at though. This contains the same pattern as even and odd, where the normal rotations are like the even elements and the flipped rotations are like the odd elements. This means that, exactly how we can simplify numbers to 0 and 1, there is a homomorphism from the dihedral group to whether an element doesn't flip or does do a flip. Maybe this is best seen with an example. We can, if we want, compute equations in D5 normally. In this example here, it results in an ordinary rotation, so one without a flip. But again, if we only care about whether an element flips or not, then we can do something simpler. Rotations don't affect whether a transformation flips or doesn't flip. Only actual flips do. So, we exactly reduce all elements to flip or no flip. Then, the simplified equation still tells us that the result has no flip. That's nice, I guess, but that's actually not the homomorphism I wanted to talk about. What if it's not the rotations that we want to ignore, but the flips? Easy, we define a new homomorphism that now keeps only an element's rotation and throws away its flip. For example, this equation here could again be calculated normally, and then be reduced to its rotation, which here is 0 rotation. Or better, we remove the flips first to get the same result. Oh no. Why did the homomorphism give a different answer now? Well, for one, we've just proven here that throwing away the flip is not a homomorphism. It clearly violates the consistency principle. But also, as unintuitive as it might seem, there is no homomorphism that simplifies down to the rotations, and we can prove that. It's time I showed you something about homomorphisms in general. Let's see what happens to the neutral element in a general group, so this is not even specifically about the dihedral group anymore. It was defined as that element which leaves any element B. Now watch what happens to it after running that equation through the homomorphism. Phi of E still leaves the other element B, but we saw last video that the neutral element is the only element that does this. So phi of E still is the neutral element in the other group. A similar thing happens with inverses. By definition, every element cancels with its inverse and returns the neutral element. When that equation gets run through the homomorphism, and since we now know that the neutral element remains the neutral element, these two new elements, whatever they might be now, are still inverses of each other. In particular, if an element happens to be its own inverse, it still must be its own inverse in the other group. So let's see what this means for us. Here we have the dihedral group, and we want to simplify it into only the rotations. But this time, instead of just defining the homomorphism blindly, let's be more smart about it and find out from the ground up what it must look like. By the first observation, the neutral element must map to the neutral element. Alright, so let's go for the flipped unit rotation. We saw before that if I animate it twice, it returns to the neutral element, meaning it is its own inverse. So, as mentioned, it must stay its own inverse in the other group. But stare at the rotations for a while and you will realize that the only self-inverse rotation is the neutral element. And there's nothing special about this flipped rotation. Visualize the pentagon in your head and check for yourself that every flipped rotation is its own inverse, so they all must map to the neutral element. So now we can give the finishing blow. Any rotation can be mimicked by a flip and then flipping back and rotating. So now we reverse engineer, and since the first two elements map to the neutral element, the ordinary rotation must too. Hence, the only possible homomorphism reduces everything down to nothing. Unfortunate. You would think elements do have an orientation, but homomorphisms claim that this is an illusion, or at least unusable. So where's this discrepancy coming from? Here's what I think is going on. There was actually never a reason for me to introduce to you the dihedral group with a horizontal flip as a standard flip. I might as well have used a slanted flip. But look, that flip turns out to be the same as the flipped unit rotation. So if I rewrite the dihedral group with that new flip, it would turn it into this. And look, some elements now have a different rotation. If a property of an element depends on how I denote my group, it's not a useful property. And homomorphisms, which are indeed independent of notation, gave us a beautiful way to explain and express how it all falls apart. I think with that, we're ready to move on to a new problem, a cute problem from cryptography. Do you remember the graph isomorphism problem from the last episode? The problem was, for two given graphs, to find out whether one can be reshaped into the form of the other. If so, these graphs are called isomorphic. They might have looked different on paper, but structurally they are the same. This phenomenon can also happen with groups. Groups can also be isomorphic. I mean, wouldn't you agree that Z5 and the rotations in D5 are the same apart from how we write them down? Both have 5 elements, and whether I write that 1 plus 2 equals 3, or that 1 unit of rotation and 2 units of rotation equal 3 units of rotation, I calculate the same equation, just in a different look. We say that there is a so-called isomorphism between Z5 and the rotations. An isomorphism is just a homomorphism, only that every output belongs to one and only one input. As a consequence, there is some ambiguity about whether an isomorphism should be defined to go from one group to the other, because it also works from the other group back to the former. Both are equally valid. And normally we can only conclude from A and B equals C that phi of A and phi of B equals phi of C, but now we can also argue backwards that phi of A and phi of B equaling phi of C must come from A and B equals C. We say that for every isomorphism in one direction, there is an inverse isomorphism, commonly denoted by phi to the minus 1 in the reverse direction. There is a reason why we use the same notation as for inverses, and you will see later why. That isomorphisms are in this sense bidirectional is what makes them so powerful. Sometimes in mathematics it happens that you have two objects, and both objects have their strengths and weaknesses. Maybe one is easier to understand but not that powerful, while the other one is more useful to us, but we don't understand it yet. If we can show that they are isomorphic, then we can take any problem from one side that we're unable to solve, move it through the isomorphism to the other side, do the calculation there, and then move the result back with the inverse isomorphism. I would like to show you an example of such an isomorphism, and for that, I'll need to introduce a new group. We are familiar with the cyclic group. For example, in Z9, we can do additions like 5 plus 6, but the result is not 11. When we count 0, 1, 2, 3, and so on, at 9, we cycle back to 0 and continue from there, so we actually get 2. We could do the same thing with multiplication. 5 times 6 is normally 30, but if we always cycle back at 9, then we also do so at 18, and then again at 27. So in the end, the result is actually 3. You would think that this makes for an interesting group. The problem is, this is not a group. The first 3 group axioms are satisfied. The system is closed, multiplication is associative, and the neutral element is 1. But not every number has an inverse. Here, the numbers 0, 3, and 6 don't have one. For 0, this is especially easy to see. There is simply no number that multiplied with 0 would ever give 1. So what do? Simple. We delete all elements that don't have an inverse. Now each element has to have an inverse. But there's one problem with this little hack. In fixing the inverse axiom, we might have broken the closure axiom. What if there's some calculation whose solution we just accidentally deleted and our system is not closed anymore? Well, it turns out that closure still holds. Amazing! Here's something that's true for every group. For any elements A and B, their product has the inverse B inverse times A inverse. A simple way to see this is to see it in action. This fact is sometimes called the socks and shoes principle. If you put on your socks and then your shoes, the way to undo that is to first remove your shoes and then your socks. Although in this group this analogy is a little bit silly, because multiplication is an operation where putting on your socks and then your shoes is the same thing as putting on your shoes and then your socks. So anyway, my point is, when we calculate 7 times 8, whatever it might be, we now know for sure that it has an inverse, namely 8 inverse times 7 inverse, and therefore it doesn't get deleted, and so closure does hold. So all in all, this is indeed a group, the so-called multiplicative group of Z9. It's denoted with the multiplication symbol, and hence is sometimes called shorter Z9 star. Multiplicative groups are obviously not restricted to Z9. Here are the groups from Z6 to Z10, and here are their multiplicative groups. Looks pretty chaotic, but the pattern behind it is actually quite simple. If a number and the number in the subscript, here 9, only share 1 as a common factor, then it is included in the group. On the other hand, in Z10, 4 and 10 both have the factor 2, so 4 gets deleted from Z10 star. That's also the reason why Z7 star still has basically all of its elements. 7 is prime, and so it can only share 1 as a factor. If you know a little bit of number theory, you can prove that this pattern indeed holds. Unfortunately, this is a series on group theory and not number theory, so I won't do this here. We won't need this fact anyway, I just thought it might help you visualize where these numbers come from. I am a big fan of this group, especially as a computer scientist. Diffie-Hellman and the RSA crypto system use it for secure message exchange, so somewhere in your phone or computer, this group is already built in. And if cryptography is famous for something, then is that it loves using primes, so computer scientists have an incentive to understand ZP star, where P is a prime. For example, here's a cool fact about squares in ZP star. First, a number is a square if it is the product of some number with itself, exactly the same as in the integers. For example, in Z11 star, 5 is a square, because it is 4 times 4, which normally is 16, but in this group cycles back to 5. Here is all of Z11 star. Remember, since 11 is prime, all the numbers from 1 to 10 are present. And here are all the squares. My cool fact about ZP star is that exactly half of the elements are squares. Always. Normally, squares become sparser and sparser the further you count up, so you would think that in some way or another something like this happens in ZP star. But no, you can try larger and larger primes, any prime except 2 for technical reasons, and you will get exactly half of the elements being squares. A cute fact. In fact, this fact eventually helped Chaffee Goldwasser, Silvio Micali, and Charles Rakoff win the Gödel Prize, which is the equivalent of the Nobel Prize, Abel Prize, for computer scientists. They needed a way to make fair coin flips over the internet, and of course the naive method doesn't work. If you just have one computer generate a random coin toss and have it tell the outcome to the other computer, there's nothing preventing it from lying. It could also just send whatever outcome is more favorable for it. If the coin toss is used for something critical, this is obviously bad. So here's an idea, a Gödel Prize winning idea. What if the computers instead each generate a random element in ZP star, send each other the result, and multiply both numbers together? Because both computers now have a say, even if one computer cheated and sent a non-random number, as long as the other number was random, the product will remain random. Now if this product is a square, the coin is set to 0, and if it is a non-square, the coin is set to 1. And each outcome has a 50% chance of happening exactly because one half are squares and the other non-squares. So why is this the case? Well, here's something really weird. ZP star is actually isomorphic to ZP-1. I find that crazy, since the two groups seem so different. One does multiplication and the other addition. But yes, here where our prime is 11, our group is nothing but Z10, just with a different look. Unfortunately, there is no obvious pattern to this isomorphism, at least I don't see a pattern. But it exists, and whenever we multiply in the multiplicative group, that calculation has an exact replica in the cyclic group. Pause the video, make your own equation, and verify that the equation in the other group indeed still holds. So now, squares which are some number being multiplied to itself correspond to numbers which are some number being added to itself. But in Z10, adding a number to itself always gives an even number, meaning every square becomes in the cyclic group an even number. Now it's quite easy to verify that half of Z10 is even, so therefore half of Z11 star are squares. It's amazing how easy this became once we knew this isomorphism and how to use it. The only question is, why does this isomorphism exist in the first place? Unfortunately, this relies heavily on the fact that P is prime, and the proof uses a lot of number theory. Again, this is a series merely on group theory, so I'll have to skip this part of the proof. But hey, at least I got to show you my favorite isomorphism.
Given a group, here the integers, an automorphism is just an isomorphism, except that it's always from a group to itself. That's it. Sounds stupid. What makes isomorphisms so amazing is that they show that two seemingly different groups are in fact the same. But of course a group is always isomorphic to itself, so what's the point of that? Well, it's not about whether a group is isomorphic to itself, but how. Because, instead of the obvious automorphism, you can also map every integer to its negative. That has the effect that every equation gets replaced with its negation, but it nonetheless remains valid. This has dire consequences. Imagine if one day aliens visit the Earth and we wanted to learn about their writing system. Even if they would convey us every single fact of the integers, from the perspective of group theory, we would not be able to decipher their symbols. To be fair, we could reconstruct the zero. When they tell us about a symbol that added to itself gives again itself, We know that this must be the 0, since 0 is the only element with that property. But apart from that, we cannot make progress anywhere. Any proposed reconstruction of an equation could just as well have come from its negation. And it's this phenomenon that automorphisms make precise. Elements that map to each other are group theoretically indistinguishable. For other groups, the situation is usually worse. Z9, for example, has not 2, but 6 automorphisms, so 6 different ways to argue with alien civilizations on what Z9 should canonically look like. By the way I found these automorphisms was that I chose a target for the one and then calculated the rest with the reverse engineering technique. Of course, this doesn't always work. We saw that if I had chosen 0 as the target, everyone's target would become 0, and this wouldn't be an automorphism. I mean, this is not even an isomorphism, it's not reversible. So what I had to do was to simply go through all the possibilities manually and note whenever it does indeed result in an automorphism. And in the end, the numbers I got were the exact same numbers from Z9 star. In other words, the automorphisms sending one to 0, 3, or 6 don't exist. And this is not unique to Z9. If we had done this with other cyclic groups, their automorphism groups would have always come out like the multiplicative group. So the question is, why? Here's where I'm trying to go with this. What automorphisms allow you to do, which wasn't possible with homomorphisms nor isomorphisms, is to chain them. Previously, our morphisms would always change equations into something different. So from then on, we either had to find a new homomorphism to apply to it, or revert with the inverse isomorphism. But now that we always remain in the same group, there's nothing stopping us from applying as many automorphisms back to back as we want. So not only do groups have the algebraic system they were designed to have, you know, the one where you can operate elements together, but there's this entire meta system on top of it, where you can operate automorphisms together. As you can probably guess, this meta system again happens to be a group. Since you've made it this far into the video, I trust you that you can verify that it indeed satisfies the 4 group axioms, so let me just briefly lose a few words on them, specifically the 2 last axioms. The neutral element of this group is the so-called identity automorphism. It maps every element to itself and is called identity exactly because the output is identical to the input. And observe, when we now combine it with some other automorphism, the overall effect is the same as doing that automorphism directly without chaining it with the identity. Or, as we write this in group theory, the identity combined with any other automorphism equals that same automorphism, exactly how a neutral element is supposed to behave. Also, I can finally explain the notation for the inverse isomorphism. Every automorphism, because it's also an isomorphism, has an inverse by definition. If the former sends A to phi of A, the latter sends phi of A back to A. So their combination is just the identity, exactly how an inverse element is supposed to behave. All in all, this group of automorphisms has the obvious name of the automorphism group, and it's written like this. As you can imagine, uncovering and analyzing the automorphism group for arbitrary groups is a big topic in group theory. But in our case, we were focusing on Z9's automorphisms. Now that we know that they form a group, could it be that the pattern we saw before is an isomorphism to Z9 star? To affirm this, let's first look at one such automorphism, for example the one that sends 1 to 2. And let's see its effect on an equation, of course with the help of reverse engineering. If 1 maps to 2, then 1 plus 1 maps to 2 plus 2, better known as 4, and 1 plus 1 plus 1 maps to 2 plus 2 plus 2, so 6. Technically, what I'm about to say is highly illegal, since groups have only one operation, and here it is addition. But in some sense, this effect is just a multiplication by 2. And there was nothing special about 2. Any automorphism scales up equations by whatever the target of 1 is. Of course, cycling back by 9 if necessary. This already hints at the connection to Z9 star, and it is strengthened if we ask. So we now know that we can combine automorphisms. What happens if we do so? If we ignore for a moment that this is about automorphisms, the answer would be simple. The act of multiplying by 2 and then by 5 might as well be a multiplication by 10. But in the context of Z9, this unfortunately doesn't make sense, because this automorphism should not exist. You cannot send 1 to 10, because 10 is not an element of Z9. Except, if I scale any number by 10, 9 of its multiples cycle back to 0. So I am left with a multiplication by 1. But that's exactly how Z9 star works. Just how any multiplications by 9 can be thrown away in Z9, so that times 10 becomes times 1, we have the same thing in Z9 star, just much more streamlined. There, 2 times 5 is just 1. That would furthermore explain why the automorphisms sending 1 to 0, 3, or 6 don't exist. Automorphisms, by definition, have an inverse automorphism, whose total effect is the identity. But 0, 3, and 6 already didn't have an inverse in Z9 star, so how are they supposed to have an inverse automorphism? The only sensible conclusion is that there aren't automorphisms in the first place. This finally demonstrates what we wanted to show, and actually, nowhere did we need the fact that this is happening in Z9. Following the same argument, one can prove that Zn's automorphism group and Zn star are isomorphic. This is the most basic but very fundamental equation in the topic of automorphisms. The cyclic group is arguably the simplest group there is, so its automorphism group is also kind of the most fundamental automorphism group of all of them. And I can kind of prove just how fundamental it is. Let's look at a more complicated automorphism group, the dihedral groups, where we use this fact and bring together all that we've learned so far. For visualization, let's do D5 and let's find every possible automorphism. We begin our reverse engineering with a unit rotation. It turns out it cannot go to a flipped rotation. Flipped rotations have the property that if I animate them twice, they return to the neutral element, while no matter what the polygon is, even if it were a mere triangle, we would need to rotate at least 3 times to get to the neutral element, if not more. Hence, the flipped rotations generally behave differently from the unit rotation, and are group theoretically distinguishable from it. Therefore, no automorphism can make them replace each other. So, let us temporarily ignore the flipped rotations. Now this is a solved problem. This is simply Z5 in disguise, where we're searching for all the possible targets of 1. This is where we now use that these automorphisms are isomorphic to Z5 star, which for us means that there are these 4 automorphisms. With that, we're already halfway done. Let's now go for the flip. No matter which automorphism we take for the rotations, they are busy mapping between themselves, so the flip can't also map to a rotation. Only other flipped rotations are possible candidates. But which ones actually work? It turns out it can go to any of them. We've seen earlier that replacing the flip with any flipped rotation is equivalent to making the flip look slanted, giving D5 an alternative look. But this is exactly where automorphisms come into play. If we, or an alien civilization, could write the dihedral group differently, then that's because there's an automorphism that maps between the original group and the same group in its new look. With that, we have found every automorphism, because now that we know where the unit rotation and the flip could map to, once we fix their targets, all other elements can be reverse engineered. Let's take a moment to reflect how far we've gotten. In the end, we've done nothing but analyze homomorphisms in this video, but it's astonishing how far a small additional property can get you each time. So where's this all going? It turns out that all this is relevant for the graph isomorphism problem. You would think that the graph isomorphism problem can be solved with, isomorphisms. The problem is that if these graphs are not isomorphic, you are in some sense stuck, because there is no isomorphism to be analyzed. But the researchers that worked on this problem used a cute trick. Instead of searching for an isomorphism between 2 different graphs, they view them as one graph with 2 components and look at that graph's automorphisms. If the 2 original graphs are isomorphic, then there is an automorphism that exchanges the 2 parts. But even if they're not, it still makes sense to talk about the automorphism group. In the worst case, this group consists of only the identity, which does nothing, but at least you've got a group to work with. This trick might sound insignificant. I mean, why even introduce an element that does nothing? But I claim that even just this is as revolutionary to the graph isomorphism problem as introducing the zero was to the entirety of mathematics. Like that, the researchers transformed the problem from a graph theory problem to an automorphism group problem, which in turn means they can now use homomorphisms to and from this automorphism group to simplify it, just how we did in the very beginning of this video. But how exactly they do that, I'll have to explain some other time.